Hello, I'm Cederwall, Professor of Experimental Nuclear Physics at KTH and responsible for the course in nuclear physics. The course is for 8 credits and includes 12 lectures and 5 lab exercises. What is nuclear physics about? This cartoon shows an artist's view of a nucleus of the isotope carbon-14, known for its use in dating of historical and archaeological objects. Nuclei consist ultimately of quarks, which are elementary particles, but they are commonly treated as bound systems of neutrons and protons. They exist on a length scale of a few femtometers and constitute more than 99.9% of the mass of the ordinary matter in the universe. Ordinary matter only represents a quite small fraction of the total mass energy in the universe, but that is a different story. Much is known about the structure of nuclei, but much is also still unknown. As a result of their small size and large mass, nuclei are extremely dense, as seen from this logarithmic plot. 3 out of the 4 known forces in nature play important roles in the nucleus: the strong, electromagnetic, and weak forces. It is the interplay between these forces that determine nuclear properties. The strong force dominates, and it is described by a theory called quantum chromodynamics, or QCD, within the so-called standard model of particle physics, as shown on this popular science wall chart. But its detailed properties relevant on the nuclear scale are still to a large extent unknown. QCD works at very high energies, but cannot, for example, predict the mass of the proton or other hadrons, and then of course not of nuclei. At the LHC, CERN, one of the main goals was recently achieved: to identify the Higgs boson, which is predicted by theory to be a consequence of the Higgs field generating the masses of the elementary particles. But the masses of protons, neutrons, and other hadrons, and therefore also of nuclei, are generated mainly from the strong interaction and not from the bare quark masses. We therefore need different and powerful experiments that can illuminate the properties of the strong interaction in the nucleus. Nuclear physics is a very active research field with billions of euros being invested in accelerator facilities and detectors around the world. We know that a few thousand different nuclei may exist, as illustrated by this chart, which shows the positions of different isotopes as a function of proton and neutron numbers. But strangely enough, only around 280 are stable or long-lived enough to remain in our environment since the solar system was created some 4.5 billion years ago. These are the black dots in this chart. One of the open questions in nuclear physics is the boundaries limiting which nuclei may exist. For this purpose, large accelerator facilities are being constructed to study more and more exotic nuclei, which are very unstable, like the International FAIR project, where Sweden and KTH are participating. It is being constructed in Darmstadt, Germany, and will be operational in a few years. At the same time, more powerful detector systems are being built with even higher precision and sensitivity the radiation being emitted from the previously unknown nuclei produced in these accelerator facilities. The AGATA gamma-ray tracking project, for which a prototype system is shown here, is one of them where KTH is strongly involved. Nuclear physics has many connections to other fields of science and many applications. A very important one is for the production of energy from fission and perhaps also in the future, fusion like in our sun. The fission process is quite complicated and not yet understood in detail. Both the dynamics of fission and the decays of the produced fission products are very important for the operation of nuclear power reactors. There are also many other applications of nuclear physics, for example in material science and in medicine, both for cancer therapy using particle accelerators and diagnostics of illness using precision nuclear techniques. For example, positron emission tomography, PET, or magnetic resonance imaging, MRI. The nuclear physics course will cover the basic properties of nuclei, nuclear decay mechanisms like alpha, beta, and gamma decay, and nuclear reactions relevant for fission, fusion, and astrophysics. It will discuss basic theory of the nucleus, introducing some simple models. Our nuclear physics knowledge will then be applied to nuclear energy production and other applications in medicine and industry. Perhaps you're curious about the origin of this mysterious glow from a nuclear power reactor and why it's important for controlling it. Welcome to the course in nuclear physics.